Next topic is significant figures. Again, as usual, the problem is we must understand what is its use. Why do we need to study this topic? It's very, very important. It's the primary question. We must be satisfied that why we are studying this topic and what is its use. What is its importance? It's very important. So, the importance of this topic is we can find the reliability. We can find the reliability of data. Method to find the reliability of our data. So now we can understand, and now it will be clear that why do we need this topic. Its importance is to check the reliability of our data, to find the reliability or to increase the reliability of data. So, number one, how rules to identify. Rules to identify significant figures. First point is introduction. I will use the word short S and F for significant figures. From now on, I will use S and F, S dot F for word significant figures. Introduction. What is significant figures? How can it be defined? There are two important parts of its definition. First, accurately known digits. Accurately known digits combination of number one, accurately known digits, and number two is first doubtful digit. Again, combination. What is significant figures? It is the combination of accurately known digits and the first doubtful digits. Next, rules to identify significant figures. Before rules, let me have an example. Might be a crude example to understand the significant figures. Let's suppose I have a scale. It's a free hand. I'm drawing the line as a free hand. Let's suppose these are the marks. Let it be 3 centimeter. Let it be 4 centimeter. It is 5 centimeter. Let it's the midpoint and it is the midpoint. Well, let's suppose you people are asked to find the length of this arrow from the above scale. Now, there are three possibilities. Let's suppose we have a classroom in which there are 3 rows. That is the first row, it's the second row, it's the third row. Students in first row will see this line a little bit in the forward position. In the second row, students will see in its exact position. The third row will see that it is laying behind. Let's suppose the students are asked to find its measurement. So the first row student might say it is something 4.7 or 4.8. They will say 4.7 and they might say 4.6. Now look at this. All the students agree at the first digits, that is 4, but they are doubtful about the second digit. So it's the first doubtful digit. This data is significant figure. Accurately known digits plus the first doubtful digit. Accurately known digit plus the first doubtful digit. So from this example might be helpful to understand the concept of significant figure. Rule number 1. All the digits other than 0 are significant. All the digits other than 0 are significant. For example, 4.231. Now look, we have 4 digits and there is all of them are non-zero digits. That is 1, 3, 2 and 4. So the significant figures are, number of significant figures are 4. Again 6.3. Again we don't have any 0, so they are all significant. Significant figures are 2. Rule number 2. 0 between the significant figures. 0 between the significant figures is also significant. Zero between the significant figures is also significant. For example, 6.103. So apply rule number 1. 3 is significant, 1 is significant and 6 is significant. Now apply rule number 2. 0 is between 1 and 3, which are significant. So this 0 is also significant. The significant figures are 4. In another example, 6.01. Apply rule number 1. 1 and 6 are significant. From rule number 2, 0 is sandwiched between the two significant figures. So it's also a significant figures. The significant figures become 3 in this case. Rule number 3. Zero to the right of significant digits zero to the right of decimal or 0 to the left of significant figures is non-significant. Again, 0 to the right of decimal or 0 to the left of significant figures is non-significant. For example, 0.0061. Now zeros to the right of decimal are non-significant, or zeros to the left of significant figures are non-significant. So they are all non-significants. We have two significant digits. Significant figures in this case are 2. Again, an example is 0.00061. As per our condition, 0 to the right of decimal, 0 to the right of decimal or 0 to the left of significant figures is non-significant. Are non-significant. If you have more than one zeros, so we will write here, are non-significant. For example, 0.00061. Now look at this. Right side, right of the decimal. From point to right of the decimal. From point to the right of the decimal. They are non-significant. And similarly, right of the decimal point, they are non-significant. Similarly, zeros at the left side of the significant figures are also non-significant. ठीक, in this case, इस केस में हम लोग के पास 2 डिजिट्स हैं जो significant हैं. Number 4th, all zeros to the right side of significant figures are significant. All zeros to the right side of significant figures are significant. For example, I have in a case, let's suppose it is 3.0000. Now, rule number 1, all the digits other than 0 are significant. Rule number 4, all the zeros to the right side, of significant figures are significant. So zeros to the right side of these 3 are significant. Significant, 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 and significant. So in this case, we have significant figures equal to 5. Okay. Again, I repeat, zeros to the right side of significant figures are significant. In the previous case, we said zeros to the right of decimal or zeros to the left of significant figures are non-significant or insignificant. Now we say zeros to the right side of significant figure are significant. For example, 3.000. In this case, we have significant figures equal to 5. Now rule number 5. In any measurement, the least count of instrument play an important role. An important role related to significant figures. For example, we have three readings: 8,000 kg, first reading. The second reading is again 8,000 kg. The third reading is again 8,000 kg. In this case, the least count is 1 kg. In this case, the least count is 10 kg. In this case, the least count is 100 kg. Now, here is a trick. In this case, the significant figures changes. In this case, the significant figures changes with the least count. In first case, we don't have any zero. In first case, we don't have any zero. So all the zeros to the right side of data are significant. In this case, significant figures become 4. Don't have any zero in the least count. So all the zeros are significant. In second case, we have 1 0. So we will not take into account the last zero. Now 2 zeros are significant. In this case, significant figures become 3. This one, and this one. In the last case, we have 2 zeros. So we will exclude 2 zeros from the significant figures. In this case, significant figures will be 2. So in this case, we say that not all the zeros to the right of the significant figures are significant. In rule number 4, we said that all the zeros at the right side of significant figures are significant. But when we are given the least count, then the rule number 4 will not apply. Again, I repeat, if we are given the least count, then the rule number 4 is not applicable. In that case, the zeros plays an important role in the number of significant figures in data. Next is significant figures in scientific notation. Significant figures in scientific notation or in standard notation. For example, in this case, the rule is all the digits with base 10 या adjacent to base 10 are significant. Significant figures in scientific notation, all the digits with base 10 are significant. Here, all the digits adjacent with base 10 are significant. For example, I'm writing here numbers 6.32 into 10 raised to power 7, 6.023 into 10 raised to power 23, 6.4 into 10 raised to power 8, and 74.3 into 10 raised to power minus 11. In first case, with base 10, we have 3 digits. So significant figures is 3. In second case, with base 10, we have 4 digits. So significant figures are 4. In third case, we have 3 digits with significant figures. That will be 3. In this case, if I say that significant figures in this case are 3, it's wrong. In this case, there are no significant figures. The reason is simply it is not a scientific notation. This is not a scientific notation, or this is not a standard notation. So you have to be vigilant in finding the significant figures, that if the data or number given is in scientific notation or non-scientific notation, the last number is not in scientific notation. Okay. Rule number 7. How to find significant figures in addition or subtraction. How to find significant figures in addition and subtraction. I will start from an example, then in the end I will write down the rule. Let's suppose we are given 4 numbers which we are supposed to add. First is 3.5 centimeter, second is 8.735 centimeters, and third is 9.73 centimeters. Now look at these numbers. The smallest, the least precise data. We have to find the least precise. Or in other words, we will look for the number which have the smallest numbers after decimal. Again I repeat. We will look for the numbers which have the smallest decimal point after decimal, which have the smallest digits after the decimal. In first case, we have 1 digit. In the second case, we have 1, 2, 3. We have 3 digits after decimal point. And in third case, we have 2 digits. So the least precise is the first data. X1 is the least precise. This is the least precise of 3. X1 is the least precise. Simply by knowing the number of digits after decimal. In this case, we have 1 digit, 3 digits, and 2 digits. The most precise is X2, after that it's X3, and the least precise X1. Now the rule is sum of the digits, or difference of the digits, sum of the data, should have sum of the data should have data sum of the data should have sum of the data should have the least should be least precise, that is number of digits after decimal. Now the sum is x1 plus x2 plus x3 is equal to, that is equal to 21.965 centimeter. But we must have a data point digit. We must have a data after point we are allowed just one digit. So we will round off this data. So we will go for the rounding of this data. We will start from 5. Before 5 it's a even number. So applying the rounding of rules, the 5 will be simply ignored. It will become 21.96 centimeter. Now we have 6. We have to round off 6. By rounding off 6, we will add 1 to the next digit. It will become 22.0 centimeter. So now look, we have one digit after the decimal. This is the least precise. So the number of significant figures in this case are 3. A bit tricky, but we have to learn. Number 8. In multiplication and division. In multiplication and division, we will go, our data should reflect, our answer should be equal to the number of least significant figures in data. Answer should have significant figures equal to the least, to the smallest significant figures in data. For example, let's suppose I have to divide two numbers, 3.2 divided by 5.42. Now look, this number have 2 significant figures and this number have 3 significant figures. From the above condition, our answer should have 2 significant figures. After division, we get a long number 0.60544280. We have to retain the 2 digits after decimal. The remaining are supposed to be round off. So we will have to round off 5, and as per rounding of rules, it will become 0.61. So the answer carries 2 significant figures. Answer should have significant figures equal to the least or smallest significant figures in data. 3.2 is divided by 5.42. 3.2 have 2 significant figures and 5.42 have 3 significant figures. So we simply reduced the quotient to 0.61.